Right now, as you read this, the whole Earth is pulling you toward its center, and you barely notice. Hold out your hand, let a coin fall, and you are watching the oldest and most familiar force there is. Of all the forces in nature, this one, the one you feel in every step you take, is also the one physics understands least well. We are going to talk about gravity, and we are going to build it up slowly, one simple step at a time, from the weight in your own feet out to the edge of the universe, where the best theories we have begin to come apart at the seams. If you like taking a large idea apart gently to see how it actually works, consider subscribing, and we will go on from here together. So let's start with one plain question that the next chapters can really answer. What is actually pulling on you? Sit still for a moment and notice your own weight. The chair pushes up against you, the floor holds your feet, and something steady and patient is pulling the rest of you down. You have felt this every second since you were born, so completely that you mostly forget it is there. Drop a set of keys and they go straight to the floor. Pour water and it falls. Trip on a step and the ground comes up to meet you faster than you would like. This pull is so ordinary that we built our whole sense of up and down around it. Up is the way things do not want to go. Down is the way they fall when you let them. We have a name for the pull. We call it gravity. And gravity is the quietest force in your life precisely because it never stops and never changes. The other forces announce themselves. A magnet snaps to a fridge, static lifts your hair, a hot stove warms your hand. Gravity just holds, evenly, without a sound, keeping the oceans in their basins and the air pressed against the planet and your blood from drifting out of your fingertips. Here is the first thing worth sitting with. The force you understand by feel, the one you trust without thinking, is the one that scientists understand the least. Not the least of the everyday forces, the least of all of them. We can predict how light behaves to more decimal places than almost anything humans have ever measured. We can describe the inside of an atom with breathtaking precision. But the gentle pull that decides whether your coffee stays in the cup is, at its foundation, the part of physics with the most unanswered questions and the most uncomfortable gaps. That is a strange place to find ourselves after more than 300 years of careful work. So this is what we are going to do. We are going to take gravity apart slowly, the way you might take apart a clock you have owned your whole life and never once opened. We will start from this feeling of weight and follow it outward, step by step, to the planets, to the stars, to black holes, and finally to the edge of the known universe, where the best theories ever written start to disagree with each other and with what we see. You do not need any mathematics to come along. You only need to be willing to hold one idea at a time and let each one settle before we reach for the next. Every chapter will answer a question that the chapter before it raised, so the climb stays gentle the whole way. Let us begin with the simplest version of the question, the one a curious child asks, and a careful physicist never fully stops asking. When you let go of the keys, what exactly is pulling them down? Not what we call it, what it is. Is the earth reaching out and grabbing them somehow across the empty space between the keys and the floor? Is the floor calling to them? Is there something invisible flowing between every heavy thing and every other heavy thing? For most of human history, people had a confident answer to that question, and the answer felt obvious, and it was wrong. It was wrong in a way that is genuinely useful to understand, because seeing why it was wrong is the first real step towards seeing what is true. The story of gravity is, in large part, the story of people slowly giving up answers that felt certain in their bodies, and trusting instead what falling objects actually do when you watch them closely. So before we meet the people who changed the picture, we should meet the picture they inherited. We should stand where the ancient world stood and look at falling things the way they did. For nearly 2,000 years, the most respected answer to why things fall came from a single thinker in ancient Greece named Aristotle. He was not a careless man. He watched the world closely, wrote about animals and weather and the stars, and built a way of explaining nature that held together so well it shaped European thought until the 17th century. When he looked at falling objects, he saw something that matches what your own eyes seem to tell you. Aristotle taught that heavier things fall faster. A stone drops quickly, a leaf drifts, a feather floats. The heavier the object, he reasoned, the more strongly it hurries toward the ground, and so the sooner it lands. This was not a wild guess. It is what you appear to see when you drop a hammer and a scrap of paper at the same time. The hammer wins, every time, and it is not close. Underneath this was a deeper idea about what the world is made of. Aristotle held that everything was built from 4 elements: earth, water, air, and fire, and that each element had a natural place it longed to return to. Earth and water belonged below, so stones and rain fell. Air and fire belonged above, so flames and smoke rose. A falling rock was not being pushed or pulled by anything outside itself. It was a piece of the element earth, going home to the centre of the world, where it was always meant to be. Notice how complete this picture is. It explains why things fall. It explains why fire climbs. It puts the earth at the centre of everything, which felt right, because the ground does not seem to move under your feet. And it agrees with daily experience so smoothly that you can see why almost no one challenged it for the better part of 2,000 years. When an idea fits your senses this well, it stops feeling like a theory and starts feeling like a plain fact about the world. But there is a soft spot in it, and the soft spot is the part about heavier things falling faster. Picture 2 stones, one heavy and one light. Drop them together and, according to Aristotle, the heavy one should clearly outrace the light one to the ground. Now tie them together with a short string and drop them as a pair. The bundle is heavier than either stone alone, so it should fall faster than the heavy stone by itself. But you could also argue the opposite. The light stone, which falls slowly on its own, should drag on the heavy one and hold it back, so the pair should fall slower than the heavy stone alone. The same rule gives you 2 answers that cannot both be true. That little knot is the loose thread. Pull it, and the whole comfortable picture starts to unravel. The trouble is that pulling on it requires something Aristotle and his followers rarely did. It requires you to stop reasoning about what falling should look like and go outside and actually watch falling things, carefully, with the willingness to be surprised. For a very long time, almost no one did. The authority of the old answer was so great that disagreeing with it felt like arrogance. The world had a centre, heavy things went to it, and that was the end of the matter. What was missing was not intelligence. It was the simple, stubborn habit of testing the idea against reality and trusting the test over the tradition. The man who built that habit into a method, and who looked hard at the loose thread, lived in Italy nearly 2,000 years later. His name was Galileo, and here's where the modern story of gravity truly begins. Galileo Galilei was born in Pisa in the middle of the 16th century, and he had a temperament that the old way of doing science could not contain. He did not want to know what the great thinkers had said about falling bodies. He wanted to drop things and measure what happened. That instinct, to trust a careful measurement over a respected opinion, is the quiet revolution at the heart of everything that follows. There is a famous story that Galileo climbed the Leaning Tower of Pisa and dropped 2 balls of different weights to prove they would land together. Historians are not sure it ever happened, and we should say so plainly rather than dress up a legend as a fact. But whether or not he used the tower, he did something far more clever, because dropping things straight down is hard to time by hand. Falling is simply too fast. So Galileo slowed gravity down. He took smooth ramps and rolled balls down them. A ball on a gentle slope rolls slowly enough that a person can mark how far it travels in equal beats of time. This let him study falling without the falling being a blur. And what he found, beat after beat, was a clean and surprising pattern. The ball did not move the same distance in each beat. It covered more ground in the second beat than the first, more again in the third, speeding up steadily as it went. Gravity, he realized, does not give an object a fixed speed. It adds speed continuously. We now call that steady adding of speed acceleration, and it is the true shape of how things fall. Then came the deeper discovery, the one that broke Aristotle. When Galileo compared balls of different weights rolling down the same ramp, they kept pace with each other. The heavy ball did not pull ahead. Stripped of the friction and the dragging of the air, a heavy object and a light object fall at exactly the same rate. The hammer beats the paper in everyday life only because the air pushes back on the wide, light paper far more than on the dense hammer. Take the air away, and they land together. You do not have to take this on faith. In the year 1971, an astronaut named David Scott stood on the airless surface of the moon, held out a hammer and a falcon feather, and let them go. They fell side by side and touched the dust at the same instant, in front of a watching world. Galileo had been right, and the moon proved it 3.5 centuries later. Carry that one plain sentence with you, because we will need it again. In the absence of air, everything falls at the same rate, no matter its weight. It is one of the strangest facts in all of physics, and we will not understand how strange it really is until much later, when a man in Switzerland asks why it should be true at all. Galileo paid a price for trusting his eyes over authority. Late in his life, for arguing that the earth moves around the sun, he was tried by the church, forced to take back his words, and made to live out his final years under house arrest. He went blind before the end, yet the method he built outlived the men who silenced him. Watch, measure, and let the measurement decide. He had shown how things fall. He had not yet said why, or what reaches across the gap to pull them. That question waited for a quiet, difficult Englishman who would look at a falling apple and think of the moon. In the years 1665 and 1666, a plague swept through England and the universities sent their students home. One of those students was a young man from a farm in Lincolnshire named Isaac Newton. Back at the family house at Woolsthorpe, with no lectures to attend and no one to interrupt him, he spent 2 of the most productive years any single human mind has ever had. He later remembered this stretch as the time when he was in the prime of his life for invention, and somewhere in it, by his own much later account, he watched an apple fall. The famous part of the story is the apple. The important part is what he did with it. Most people who see an apple drop think nothing of it. Newton asked a question that almost no one had thought to ask. The apple falls toward the earth. The moon hangs in the sky and does not fall. What if the moon is falling too? Hold on to that, because it is the leap. The moon, Newton reasoned, is not sitting still up there, and it is not held by some special heavenly rule. It is moving sideways, fast, and at the same time it is being pulled toward the earth, exactly as the apple is pulled. The sideways motion and the downward pull combine so that the moon keeps curving around the earth instead of flying off in a straight line or crashing down. It is forever falling toward us and forever missing, because it is also racing past us. An orbit, in Newton's picture, is just falling that never ends. Imagine throwing a stone. Throw it gently and it lands a few steps away. Throw it harder and it lands farther off, the path a longer curve. Now imagine throwing it so hard that the curve of its fall matches the curve of the Earth itself. The stone keeps falling, but the ground keeps dropping away beneath it at the same rate, and the stone circles the whole planet and comes around behind you. That is an orbit. The moon is a stone thrown so perfectly that it has been falling around us for billions of years. The truly daring step was to insist that it is the same pull in both cases. The same force that drops the apple in the orchard reaches all the way to the moon and holds it in its path. Earthly gravity and heavenly motion are not two different things ruled by two different laws. They are one thing. This was the first time anyone had dared to say that the rules in the sky and the rules on the ground are the same rules. It united the heavens and the earth in a single sweep, and it was a genuinely shocking thing to claim. Newton did more than claim it. He tested it with numbers. The moon is about 60 times farther from the centre of the earth than the apple in the orchard is. If gravity weakens with distance in a particular way, then the pull on the moon should be far gentler than the pull on the apple, gentle enough to bend the moon's path by just the right amount over a month. He worked out how much the moon should curve if his idea was right, and compared it to how much the moon actually curves, which astronomers had measured. The two roughly agreed. That agreement was the seed of everything. It meant the falling apple and the orbiting moon really might obey one universal rule. But a rough agreement is not a finished law. To turn his insight into something exact, Newton needed to say precisely how the pull changes with distance and with the masses involved. He needed to write the rule down as a single equation that would work for the apple, the moon, the planets, and everything else at once. That equation, when it came, would be one of the most powerful sentences ever written. The man who pushed Newton to write it all down was an astronomer named Edmund Halley, the same Halley remembered for the comet. In the year 1684, Halley came to Cambridge with a question that was troubling the cleverest minds in London. If the sun pulls on a planet with a force that weakens with the square of the distance, what shape should the planet's path be? Newton answered at once, almost offhandedly, that it would be an ellipse, a stretched circle, and that he had worked this out years before. Halley was astonished, and he urged Newton to set the whole thing down properly. The result, 3 years later, was a book in Latin whose short name is the Principia, and it is one of the most important books ever written. In it, Newton stated his law of universal gravitation in a single sweeping idea. Every object in the universe pulls on every other object. The sun pulls the earth pulls the moon, the earth pulls you, and, far more faintly, you pull the earth back. There is no special heavenly substance and no privileged centre. The same rule binds a falling apple, an orbiting moon, a comet swinging in from the dark, and two coins resting on a table, which pull on each other with a force far too small to notice. The rule has two simple parts. First, the pull grows with mass. The more matter in the two objects, the stronger the attraction between them. The sun is so vast that it holds planets across billions of kilometres of empty space. Second, the pull weakens with distance, and it weakens in a precise way that Newton called the inverse square. Move twice as far apart, and the pull drops not to half but to a quarter. Move 3 times as far, and it falls to a ninth. The strength fades with the square of the distance between the two centres. There is a clean way to picture why a square appears. Imagine the pull of an object spreading outward in every direction, like light from a bare bulb. As you move away, that same influence has to cover the surface of a larger and larger sphere. The surface of a sphere grows with the square of its radius, so the influence reaching any one patch thins out by the same square. The inverse square law is, in a sense, just the geometry of things spreading out evenly into space. With this one law, Newton could do what no one had done before. He could explain why the planets trace ellipses around the Sun, which the astronomer Johannes Kepler had discovered as a pattern but could not account for. He could explain the tides as the Moon and Sun tugging the oceans. He could explain why the Earth bulges slightly at its middle from its own spin. The same equation handled the small and the immense, the everyday and the astronomical, all at once. It was the first time a single human sentence had reached from the kitchen table to the edge of the solar system. For more than 200 years, this law was as close to perfect as science had ever come. Spacecraft we launch today still use Newton's gravity to coast to other planets, because for most purposes it is exactly right. When you hear that a probe arrived at Jupiter on schedule after a journey of years, you are watching Newton's law keep a promise made in 1687. And yet, tucked inside that triumphant equation, there was a quiet gap that Newton himself could not close. His law told you how the pull between two objects compares to the pull between two others. It let you weigh the planets against each other, but it could not, on its own, tell you the actual strength of gravity in plain units, the real force in your hand when you hold an apple. To pin that down, the law needed one more number. And that number turned out to be remarkably, almost absurdly, hard to find. To see what was missing, look closely at Newton's law as a recipe. It says the gravitational pull between two objects depends on their masses multiplied together, divided by the square of the distance between them. But a recipe like that gives you a proportion, not a finished amount. It tells you that doubling a mass doubles the pull, and that doubling the distance quarters it. It does not tell you how much pull you get to begin with. Somewhere in the recipe there has to be a fixed conversion, a number that turns masses and distances into an actual force you could measure with a scale. That number is the gravitational constant, written as a single letter, big G. Here is the subtle thing, and it is worth slowing down for. You can do an enormous amount of astronomy without ever knowing G. You can compare the planets, map their orbits, and predict eclipses, because in all of those cases gravity is being weighed against gravity, and the unknown constant cancels itself out of both sides. Newton could tell you that the Sun is far more massive than the Earth, and by how much as a ratio. What he could not tell you was the mass of the Earth in everyday units, in something like kilograms, because to get there you have to know the real strength of the pull, and that means knowing G. So why was it so hard to measure? The answer is the same fact we are circling throughout this whole story. Gravity is fantastically weak. To find G directly, you cannot use the Earth, because you do not yet know the Earth's mass, which is the very thing you are trying to reach. You have to measure the gravitational pull between two ordinary objects you can hold, two metal balls in a room, and then read off how strongly they attract each other. The trouble is that the attraction between two metal balls is so tiny that almost anything will drown it out. A faint draught of air, a small change in temperature, the warmth of your own body across the room, the slight tilt of the floor, any of these can swamp the whisper of gravity you are trying to hear. Think of it this way. The entire Earth, a ball of rock 8,000 miles across, pulls on a coin in your hand just hard enough to make it weigh a few grams. Now shrink the Earth down to a cannonball sitting on your table. The pull that cannonball exerts on the coin is so slight that you would never feel it, never see it, never know it was there without an instrument of extraordinary delicacy. To measure G is to measure that whisper, and to measure it cleanly while the whole loud world leans in around you. Newton understood the problem and thought it might be hopeless. He once estimated that two large objects placed near each other would pull together so feebly that the effect could never be detected on a human scale. He could write the most successful law in the history of science and still believe that one of the numbers inside it lay forever out of reach. There is something humbling in that. The man who weighed the heavens against each other did not think anyone would ever weigh the earth itself. He was wrong, but it took a long time and a very particular kind of person to prove it. More than a century after Newton's apple, a wealthy, painfully private Englishman set up an experiment of such care that he managed to feel the pull between two lead balls and, from that whisper, weigh the entire planet. We turn to him next. Henry Cavendish was one of the strangest figures in the history of science, and one of the most precise. He was born in 1731 into a family of great wealth, and he had no need to work for a living, which left him free to spend his days on experiments. He was also extraordinarily shy, so shy that conversation seems to have been painful for him. He could barely speak to women at all, and is said to have communicated with his female servants by leaving written notes. He dined alone. He avoided gatherings. What he did instead, for decades, was measure the world with a patience few people have ever matched. The experiment that made him immortal was not even his own idea at the start. A clergyman and scientist named John Michell had designed a delicate instrument to weigh the earth, but died before he could use it. The apparatus passed to Cavendish, who rebuilt it and carried it out in the year 1798, when he was 67 years old. The device is now called a torsion balance, and its genius is that it turns a force too small to feel into a motion you can see. Picture a light wooden rod hung from its middle by a thin fibre, so that it can twist freely, like the needle of a compass made to spin sideways. On each end of the rod sits a small lead ball. Now bring two much larger lead spheres close to the small ones, one on each side, positioned so their gravity tugs the little balls gently sideways. The pull is minute, but it twists the fibre by a tiny angle, and the rod slowly turns. By measuring how far it turns and how stiff the fibre is, Cavendish could work out the exact strength of the gravitational attraction between the large and small balls. The care this required is hard to overstate. The twist he was measuring was so small that the heat of a candle or the stir of the air would ruin it. So Cavendish enclosed the whole apparatus in a sealed case, set it in a closed room, and observed it from outside through a telescope, so that his own body heat would not disturb the result. He let the room settle for long periods. He watched the slow swing of the rod and timed it. He was, in effect, listening for the faintest sound in physics while holding his breath. From the size of the twist, Cavendish could calculate the density of the Earth, which is how he himself described the result. He found that the Earth is about 5.5 times as dense as water. That single number combined with the known size of the planet gives you the mass of the Earth, and from the mass you can recover the gravitational constant. He had weighed the world. The figure he arrived at for the Earth's density is within about 1% of the value we accept today, more than 2 centuries later. With 2 lead balls and a thread, in a quiet room, a reclusive man had measured one of the deepest numbers in nature. What makes this so remarkable is not just the cleverness, but the result's staying power. For a long time, no one could do meaningfully better. The torsion balance Cavendish refined remained, in spirit, the best tool we had for measuring the strength of gravity, and that fact will return to haunt us later, because it points at something uncomfortable. Of all the fundamental numbers in physics, this is the one we have struggled hardest to pin down, and the struggle is not over. Before we feel the full weight of that struggle, though, we should ask what Cavendish's number actually tells us about gravity. It tells us, above all, just how astonishingly feeble this force really is. Let us put a face to the gravitational constant, the number Cavendish first pinned down. Written out, big G is about 6.67, followed by a tiny scaling that pushes it 11 decimal places below 1. You do not need to remember the digits. You only need to feel what such a small number means. It means that when you multiply two masses together and divide by the distance between them, you then shrink the answer by an almost unimaginable amount before you get the actual force. Gravity, in other words, comes with a built-in volume knob turned very nearly all the way down. We can make this concrete with a comparison you can hold in your mind. Take a single proton and a single electron, the particles inside an atom. They pull on each other through gravity because they have mass, and they also pull on each other through the electric force because they have charge. Now ask how those two pulls compare. The electric force between them is stronger than the gravitational force by a factor with around 40 zeros after it. 40 zeros. If you tried to write that number out, it would be one followed by enough zeros to run off the edge of the page. Gravity between two particles is not just weaker than the electric force. It is so much weaker that it barely deserves to be in the same sentence. This raises an obvious puzzle. If gravity is the runt of the forces, why does it feel like the boss of your daily life? Why can it pin you to a chair, hold the moon and crush stars when it loses to a fridge magnet by 40 orders of magnitude? A small fridge magnet, after all, lifts a paperclip clean off the table, which means that scrap of magnet is, in that moment, outpulling the entire Earth. The answer is that gravity has one quiet advantage that none of the other forces share. It only ever adds. The electric force comes in two flavours, positive and negative, and in any large object the positives and negatives almost perfectly cancel, leaving the whole thing electrically neutral. Your body and the floor are both swarming with charges, but those charges balance out, so the electric force between you and the floor nets to nearly nothing. Gravity has no opposite. There is no negative mass to cancel positive mass. Every speck of matter pulls on every other speck, and all those tiny pulls pile up in the same direction without ever subtracting. So gravity wins by sheer accumulation. The pull from any one atom of the Earth on you is hopelessly weak, but the Earth has a number of atoms with about 50 zeros in it, and every single one of them pulls you downward, and none of them pulls you up. Add 50 zeros worth of feeble tugs that never cancel, and you get the steady, commanding weight you feel right now. The force loses every fair fight between particles and wins the war only because it can muster the whole planet on its side. This is why gravity rules the large universe while hiding in the small one. In an atom, it is irrelevant. Across a laboratory bench, it is a whisper that took a genius to detect. But out among stars and galaxies, where objects are too big to hold a net charge and the other forces have long since cancelled or run out of reach, gravity is the only force still standing. It shapes everything on the larger scales precisely because it is patient, one-directional, and never lets go. Hold that image, because it explains the shape of the rest of our story. The everyday pull, the orbiting moon, the structure of galaxies, all of it is the same faint force adding up. And for 2 centuries, Newton's version of that force passed every test we threw at it. Then a single planet, the one closest to the Sun, began to misbehave in a way that no amount of hidden mass could quite explain. The planet was Mercury, the small fast world closest to the Sun. Like every planet, Mercury traces an ellipse, a slightly stretched circle, and the long axis of that ellipse slowly swivels around over time, like the hand of a clock that takes ages to come around. This swivelling is called precession, and Newton's law predicts most of it neatly, because the other planets tug on Mercury and nudge its orbit along. Astronomers added up all those tugs with great care and got a number for how fast Mercury's orbit should turn. It did not match. Mercury's orbit turned a little faster than Newton's law allowed. The gap was tiny, a sliver of an angle accumulating over a century, far too small to see by eye, but far too large to ignore once you measured it. And in physics, a tiny gap that refuses to close is often the first sign of something deep. The most successful law in science was off by a sliver in the place closest to the Sun. The astronomer who sharpened the problem was a Frenchman named Urbain Le Verrier, and he had every reason to trust Newton, because Newton had already made him famous. Years earlier, the planet Uranus had been wandering slightly off its predicted path, and Le Verrier had guessed that an unseen planet farther out was pulling on it. He calculated where that hidden planet must be, and astronomers pointed a telescope at the spot and found Neptune almost exactly where he said it would be. It was one of the great triumphs of Newton's gravity, a new world discovered with a pencil before anyone laid eyes on it. So when Mercury misbehaved, Le Verrier reached for the same explanation that had just worked so spectacularly. There must be another hidden planet, he reasoned, this time tucked between Mercury and the Sun, too close to the glare to spot, tugging Mercury's orbit forward. He even gave it a name, Vulcan, after the Roman god of fire, fitting for a world baking next to the Sun. The hunt for Vulcan was on. Astronomers searched the Sun's edge during eclipses, and now and then someone announced a sighting. But the sightings never held up. Vulcan was never there. This is a moment worth pausing on, because it shows how science actually works when a trusted theory begins to fail. The first instinct, the right instinct, is not to throw the theory away. It is to assume the theory is fine, and that something is missing from the picture. Some unseen mass, some overlooked tug. That instinct had just found Neptune. It was a good instinct. But this time the missing planet was a phantom, and no amount of searching the Sun's edge would conjure it into being. The discrepancy in Mercury's orbit was real, it was stubborn, and it could not be patched by adding a hidden world. Keep that pattern in mind, because we are going to meet it again and again before this story is done. A beautifully successful theory makes a prediction. The prediction is slightly off. Scientists first try to save the theory by adding something unseen, a new planet, a new kind of matter, a new form of energy. Sometimes the unseen thing turns out to be real, and the theory is vindicated. Sometimes the unseen thing never appears, and the small discrepancy turns out to be the theory itself quietly announcing its own limits. Telling those two cases apart is one of the hardest things in all of science, and it is exactly the knot that scientists are wrestling with about gravity right now. For Mercury, the discrepancy was the second kind. The problem was not a missing planet. The problem was that Newton's picture of gravity, for all its power, was not quite the final truth. It was an extraordinarily good approximation that broke down ever so slightly in the strongest gravity in the solar system, right next to the Sun. To close that sliver of a gap, the world would need an entirely new idea of what gravity is. Not a stronger pull or a hidden world, but a different picture altogether. That picture came from a patent clerk in Switzerland, and it began not with planets, but with a falling man. Around the year 1907, a young man named Albert Einstein was working in a patent office in Bern, Switzerland, examining other people's inventions and thinking, in his spare hours, about the deepest problems in physics. He had no university post and no laboratory. He had a desk, a steady job, and a mind that would not let certain questions go. One day, by his own later account, he had what he called the happiest thought of his life. It was this: a person falling freely does not feel their own weight. Sit with that, because it sounds almost too simple to matter. Imagine you are in a lift and the cable snaps, so the lift and everything in it fall together. In those terrifying seconds, you would float inside the falling box. If you let go of your keys, they would not drop to the floor, because the floor is falling just as fast as the keys. For that brief doomed moment, gravity would seem to vanish. You would be weightless, exactly like an astronaut drifting in orbit, who is in truth simply falling around the Earth and never landing. Einstein turned this everyday observation into a principle. Being in free fall, he said, is indistinguishable from floating in deep space with no gravity at all. And the flip side is just as powerful. Standing on the Earth feeling your weight is indistinguishable from standing in a rocket far out in space that is accelerating upward, pressing the floor against your feet. Inside a sealed room, with no window, you could not tell whether you were being held down by a planet's gravity or pushed by a rocket's thrust. The two situations feel exactly the same because, Einstein proposed, they are at heart the same thing. This is the equivalence principle, and it is the seed of everything that follows. Now recall the strange fact we set aside long ago, the one we said we would need again. Galileo found that all objects fall at the same rate regardless of their weight. The hammer and the feather landing together on the moon. In Newton's framework, this is a curious coincidence that just happens to be true. In Einstein's, it stops being a coincidence and becomes the whole point. If gravity and acceleration are the same, then of course everything falls together, because falling is not really objects being pulled at different strengths. It is everything simply following the same motion through something deeper. That something deeper is what Einstein spent the next 8 years building, in the hardest intellectual labour of his life. He had the key idea by 1907, but turning it into a complete theory took him until 1915, and it nearly broke him. He had to learn new and difficult mathematics, make false starts, and follow the principle into territory no one had mapped. The equivalence principle told him that gravity was somehow about motion and geometry rather than a force reaching across space, but it did not yet tell him what was doing the bending. The answer he arrived at was so strange that it still takes effort to accept, even knowing it is true. Gravity, Einstein concluded, is not a force pulling objects across empty space at all. There is no invisible cord between the Earth and the Moon. Instead, mass changes the shape of space and time around it, and objects simply move as straight as they can through that changed shape. The falling man, the orbiting moon, the planet Mercury, none of them are being pulled. They are all just following the lay of the land in a landscape we cannot see. To understand what that means, we have to look closely at the thing Einstein said was bending. Not just space, but space and time woven together, and the way that mass curves them. For 200 years, space was thought of as an empty stage, a fixed and changeless backdrop where the events of the universe played out, and time was a steady clock ticking the same everywhere, indifferent to everything. Einstein dissolved that picture. Space and time, he showed, are not separate, and they are not fixed. They are woven into a single fabric which we call spacetime, and that fabric can stretch, curve and bend. Mass and energy are what do the bending. And what we have always called gravity is simply matter following the curves. The picture almost everyone reaches for is a stretched rubber sheet. Imagine a taut trampoline. Set a heavy bowling ball in the middle, and the surface sags into a deep bowl around it. Now roll a small marble across the sheet. As it passes the dip, its path curves inward toward the ball, not because the ball reaches out and grabs it, but because the surface it is rolling on is no longer flat. If you give the marble the right speed, it will circle the dip again and again, like a planet around a star. The ball is not pulling the marble, the ball has bent the surface, and the marble is just going straight across a curved world. That image is genuinely helpful, and it captures the heart of the idea. A massive object like the sun curves the space-time around it, and the Earth moving as straight as it can through that curved space-time. Traces a great circle that we see as an orbit. There is no chord, no reaching, no pull in the old sense. There is only shape, and motion through shape. Hold on to that one plain sentence. Matter tells space-time how to curve, and curved space-time tells matter how to move. But we promised, every time we lean on a comparison, to show you where it stops fitting, because the edge is where the real physics lives. The trampoline picture has two honest flaws. First, it is cheating a little, because it uses gravity to work. The bowling ball makes the dip only because the Earth's own gravity pulls it down into the sheet. The picture explains gravity by quietly assuming gravity, which means it cannot be the true cause. It is a memory aid, not an explanation. The second flaw is deeper, and it is the part almost every version of this story leaves out. The trampoline shows space bending, a two-dimensional sheet sagging into a third dimension. But the most important bending in Einstein's theory is not the bending of space. It is the bending of time. Near a massive object, time itself runs slower. A clock at sea level ticks very slightly slower than a clock on a mountaintop, because it sits deeper in the Earth's gravity. This is not a trick of the clocks. Time genuinely passes at different rates at different heights, and we have measured it. And here is the quiet revelation. When you drop your keys, the main reason they fall is not that space is curved beneath them. It is that time runs a little slower closer to the floor, and the keys, moving as straight as they can through space-time, naturally veer toward where time runs slow. You fall because, in a sense, the future is downward. The everyday weight you feel in your chair, the whole familiar pull of gravity, is in large part the bending of time, not the bending of space. The trampoline never shows you that, which is why it can never quite tell you the truth. This was a breathtaking claim, beautiful and strange, and Einstein finished it in 1915 as the First World War tore across Europe. The first thing it had to do was settle the old debt. It had to explain Mercury, the sliver of orbit that Newton could not account for, and that the phantom planet Vulcan never fixed. It did. When Einstein worked out how Mercury would move through the curved space-time near the heavy sun, the extra swivel in its orbit fell out of the equations exactly, with no hidden planet required. He later said the discovery gave him heart palpitations. His new picture of gravity had healed the old wound on its very first try. But explaining something already known is only half a test. To truly convince the world, the theory had to predict something no one had seen, and then be proven right under the open sky. The bold new prediction was about light. If mass curves space-time, Einstein reasoned, then even a beam of light, passing close to a massive object, should follow the curve and bend. Light has no weight in the old sense, so under Newton's law it should sail straight past the sun untroubled. But in Einstein's universe, the sun bends the space-time around it. An array of starlight grazing the sun's edge must veer as it crosses that warp, like a cart steering around the rim of a valley. Einstein even calculated the exact angle of the bend, a tiny deflection, but a definite one, and twice as large as Newton's law would grudgingly allow. The trouble is that you cannot normally see a star whose light skims past the sun, because the sun is blindingly bright and drowns out everything near it. There is only one moment when the sun's face is blacked out and the stars beside it become visible. A total solar eclipse. During those few minutes of darkness, you could photograph the stars near the sun's edge and check whether their light had been bent by seeing if they appeared shifted from their normal positions. If the shift matched Einstein's number, gravity bends light and spacetime is real. The man who set out to test this was an English astronomer named Arthur Eddington, and his situation was delicate. It was 1919, just after the First World War, and Einstein was German while Eddington was British. The two nations had been slaughtering each other for 4 years. For an Englishman to mount an expensive expedition to confirm the theory of a German was, to some, almost unpatriotic. But Eddington was a Quaker, a pacifist, and he believed that science should heal the wounds nations inflict, not deepen them. Proving Einstein right, across enemy lines, was for him a kind of reconciliation. So in 1919, Eddington led an expedition to the island of Principe, off the coast of West Africa, while a second team went to Brazil to photograph a total eclipse from 2 places at once. On the island, the morning of the eclipse brought clouds and rain, and Eddington must have feared the whole effort was lost. But the sky cleared just enough at the crucial moment, and he captured his photographs of the darkened sun ringed by stars. Then came the slow, painstaking work of measuring the star positions on the plates and comparing them to where those stars sat in the ordinary night sky. The stars had shifted. Their light had been bent as it passed the sun, and bent by close to the angle Einstein had predicted, the larger amount his theory demanded rather than the smaller one Newton allowed. When the result was announced in London that November, it made headlines around the world. Newspapers declared that the heavens were warped and that a new figure had overturned the great Newton. Almost overnight, Einstein became the most famous scientist alive, a household name far beyond physics, because a quiet English astronomer had pointed a camera at an eclipse and watched starlight bend. It is worth being honest about the history. Eddington's measurements were near the edge of what his instruments could resolve, and some later critics argued he leaned toward the result he hoped for. But the eclipse test has since been repeated many times with far better equipment, and gravity's bending of light is now measured routinely and confirmed with great precision. We even use it as a tool. Distant galaxies act as giant lenses, their mass bending the light of things behind them into arcs and rings, a phenomenon we call gravitational lensing, and it is now one of the most powerful instruments in astronomy. Einstein's strange idea became an everyday lens on the cosmos. So by the early 20th century, gravity had been remade. It was no longer a pull but a curvature, and that curvature had been caught bending starlight under an eclipsed sun. The same theory that explained the apple and the moon now reached out to shape light itself. And once you accept that mass bends space-time, a far larger question opens up, almost against your will. If matter curves the space around it, then what is the shape of all the matter in the universe doing to space as a whole? What is the shape of everything? When Einstein turned his equations on the entire universe, he found something he did not want to find. The mathematics insisted that the universe could not simply sit still. A cosmos full of matter, with every piece pulling on every other piece through curved spacetime, should be either expanding or collapsing, like a ball thrown upward that must be either rising or falling, but never frozen in the air. Yet everyone in 1917, Einstein included, took for granted that the universe was eternal and unchanging, a fixed stage of stars. So he did something he would come to regret. He added a term to his equations, a kind of built-in pressure spread through empty space, tuned precisely to hold the universe still. He called it the cosmological constant, and we still write it with the Greek letter lambda. It was a fudge, and a brilliant one, but it was wrong, and the man who showed it was wrong started from the equations alone. A Russian mathematician named Alexander Friedmann took Einstein's theory at face value, without the steadying term, and worked out that it allowed a whole family of expanding and contracting universes. Einstein at first dismissed the work as a mathematical error, then grudgingly admitted it was sound, but insisted it had nothing to do with reality. Friedmann died young, of typhoid, at 37, never knowing that his expanding universe was the real one. The same conclusion was reached independently by a Belgian named Georges Lemaitre, who had the unusual distinction of being both a trained physicist and an ordained Catholic priest. Lemaitre not only found the expanding solutions, but took them seriously as a description of the actual cosmos. If the universe is expanding now, he reasoned, then running the film backward, it must have been smaller and denser in the past, and smaller and denser still further back, until everything was packed into a single dense beginning. He called it the primeval atom. We now call the whole picture the Big Bang, and it began as a priest following Einstein's gravity to its honest conclusion. The proof came from the sky, through an American astronomer named Edwin Hubble, working with the largest telescope in the world on a mountain in California. Hubble was measuring the light of distant galaxies, and he noticed that the light from nearly all of them was stretched toward the red end of the spectrum, a shift that happens when something is moving away from you. More than that, the farther away a galaxy was, the faster it was receding. This is exactly what you would see if the whole universe was swelling outward. Every galaxy carried apart from every other as the space between them grows. Hubble had caught the expansion in the act. The discovery undid Einstein's fudge. The universe was not static after all, so it had never needed the steadying term he had forced into his equations. He is said to have called the cosmological constant the biggest blunder of his life, because if he had only trusted his original equations, he could have predicted the expanding universe years before Hubble found it. He let a stubborn assumption about a fixed cosmos override what his own theory was telling him. But hold that word, blunder, lightly and keep the cosmological constant in the back of your mind. We are going to set it aside now, the way Einstein tried to. Decades later, it will come walking back into the story uninvited, not as a fudge to hold the universe still, but as a genuine and deeply puzzling feature of reality, tied to one of the things scientists are most unsettled about today. The term Einstein invented to make the universe behave will turn out to describe something real that we still cannot explain. For now, the lesson is that gravity does not just hold moons and bend starlight. On the largest scale, gravity decides the fate of everything, whether the universe expands forever or one day falls back together. And if gravity governs the whole cosmos, we should look at the place where gravity is not gentle at all, where it overwhelms every other force and bends spacetime until it tears. We should look at what happens when gravity wins completely. Within months of Einstein publishing his theory of gravity in 1915, a solution to his equations arrived from an unexpected place: the Russian front of the First World War. A German physicist named Karl Schwarzschild was serving in the army, calculating artillery trajectories and in the trenches while ill. He found time to solve Einstein's equations for the spacetime around a single round mass. It was the first exact solution anyone had found, and it was elegant. But buried inside it was something monstrous. Schwarzschild died of an illness a few months later, never living to see what his solution truly described. His mathematics said that if you squeezed enough mass into a small enough space, the curvature of space-time near it would grow without limit. There would be a boundary, a certain distance from the centre, where the bending of time became so extreme that nothing could climb back out, not even light. Cross that boundary, and every possible path forward leads inward. We now call that boundary the event horizon, and we call the object it surrounds a black hole. The name came much later, but the thing itself fell straight out of Einstein's gravity within a year of its birth. Think back to what we said about why you fall. You drift toward where time runs slow. Near an ordinary planet, time runs only slightly slower at your feet than at your head, so the pull is gentle. But pile up enough mass in a small enough region, and the slowing of time becomes savage. At the event horizon, from the outside, time appears to stop altogether. Inside, the curvature is so total that the direction we call the future points inward, toward the centre. Escaping a black hole is not like climbing a steep hill. It is like trying to travel into yesterday. The geometry simply does not allow it. For decades, most physicists, Einstein among them, refused to believe such things could really exist. They looked like a mathematical disease, an absurdity that surely could not occur in the actual universe. Surely some force would always halt the collapse before it reached such an extreme. But as the 20th century went on, the case grew stronger. We learned how stars work, and we realized that when a massive star runs out of fuel and can no longer hold itself up against its own gravity, nothing remains to stop the fall. The core collapses, the mass crushes inward past every barrier, and a black hole is born. Gravity, the weakest force, the runt of the family, finally has its way completely. And the evidence has poured in. We have watched stars whip around an invisible something at the centre of our own galaxy, orbiting so fast that whatever they circle must be millions of times the mass of the Sun, packed into a region smaller than our solar system. There is no known object that can be except a black hole. We have in recent years even made images of the glowing gas swirling around two of these giants, a dark silhouette ringed by light, looking eerily like the predictions. The monster in Schwarzschild's wartime equations is real, and the sky is full of them. But notice what we have done. We have followed gravity to a place where it bends time to a standstill and crushes matter past all limits. And right at the centre, the theory does something alarming. Einstein's equations, pushed to the heart of a black hole, do not give a sensible answer. They give infinity. The curvature is predicted to become endless, the density to become endless, in a single point of no size at all. That is not a description of a thing. It is the sound of a theory breaking. When a theory predicts infinity, it is usually confessing that it has reached the end of what it can describe. And that confession, hidden at the centre of every black hole, is the first deep crack in Einstein's gravity itself. The word for that breaking point is singularity, a place where the quantities in the theory shoot to infinity and the equations stop meaning anything. For a long time, physicists hoped the singularity was an illusion, an artifact of assuming a black hole was perfectly round and smooth. Real stars are lumpy and spinning, the reasoning went, so maybe a real collapse would miss the exact centre, swirl around, and avoid the catastrophe of a true point of infinite density. The singularity, they hoped, was a flaw in the idealized picture, not a feature of reality. A young British mathematician named Roger Penrose closed that escape route in 1965. Using a new and powerful style of reasoning about the shape of spacetime, he proved that the singularity was not a fluke of perfect symmetry. Once a collapse passes a certain point and an event horizon forms, a singularity must follow, no matter how lumpy or off-centre or spinning the original star was. The infinite centre was not an accident you could dodge. It was woven into the logic of Einstein's own theory. For this work, Penrose received a share of the Nobel Prize in Physics more than 50 years later in 2020. Then Penrose joined forces, in a sense, with a young physicist named Stephen Hawking, who turned the same powerful reasoning in the opposite direction toward the beginning of time. If you run the expanding universe backward, everything grows denser and more curved until you reach the very first moment. Hawking showed that the same mathematics forcing a singularity at the centre of a black hole also forces one at the birth of the cosmos. The Big Bang, in this light, is not just a hot, dense early state. According to Einstein's gravity taken at its word, it is a singularity, a moment of infinite density where the theory once again breaks down and tells us nothing. Sit with how serious this is. Einstein's theory of gravity is one of the most successful descriptions of nature ever written. It explained Mercury, bent starlight, predicted the expanding universe, and conjured black holes that we have since seen. And yet that same theory, pushed to two of the most important places in all of physics, the centre of a black hole and the first instant of the universe, does not merely struggle. It self-destructs. It hands back infinity, which is mathematics raising its hands and admitting it has run out of road. This is the heart of why gravity remains unfinished business. A theory that predicts its own breakdown is telling you that it is not the final word, that something deeper must take over where it fails. Newton's gravity broke down in the small sliver of Mercury's orbit, and Einstein's richer theory grew out of that crack. Now Einstein's theory breaks down at singularities, and that crack is a sign that an even deeper theory of gravity must lie beneath it, one we do not yet have. There is a strange comfort hidden here though, and it is worth naming. The infinities are not where we live. The centre of a black hole is sealed behind a horizon, and the first instant of the universe is far behind us. For almost everything we care about, Einstein's gravity works flawlessly, and the breakdown stays safely out of reach. A bridge can be perfectly sound for crossing, even if it would fail under a weight no one will ever place on it. So the singularities did not send anyone into a panic. They were a known flaw, filed away as a problem for the distant future. What did not stay filed away was another prediction lurking in Einstein's equations, one he made and then doubted, then made again. If mass curves spacetime and masses move, then the curvature should move too. Shake a heavy thing, and the bending of spacetime around it should ripple outward, like a disturbance spreading across a pond. Einstein predicted these ripples, called them gravitational waves, and then spent years unsure whether they were real or just a quirk of his mathematics. Settling that doubt would take a full century and an instrument of almost impossible delicacy. A gravitational wave is at heart a ripple in the shape of spacetime itself, spreading outward at the speed of light. When two heavy objects whirl around each other, they stir the spacetime around them, and that stirring travels off into the universe as a wave that alternately stretches and squeezes space as it passes. If such a wave washed over you, you would, for the briefest instant, grow very slightly taller and thinner, then slightly shorter and wider as space itself flexed. You would never feel it. The effect is unimaginably small. Einstein predicted these waves in 1916, soon after finishing his theory, and then spent 2 decades unsure. At one point in the 1930s he wrote a paper arguing that gravitational waves did not really exist, that they were a mathematical illusion. A journal editor sent the paper to a reviewer who found an error. Einstein was offended at the very idea of being reviewed, and he withdrew it in anger, only for a colleague to gently show him the mistake. The waves were real in the theory after all. But even Einstein doubted that anything so faint could ever be detected, and on that point he had good reason for doubt. The faintness is the whole problem, and it is staggering. By the time a gravitational wave from some distant cosmic violence reaches Earth, the stretching and squeezing it causes is smaller than the width of a proton across the entire span of a detector kilometers long. You are trying to measure a change in length thousands of times smaller than the nucleus of a single atom. For most of the 20th century, this seemed not merely difficult, but absurd, a precision so fine that no instrument could ever hope to reach it. The waves were a beautiful consequence of Einstein's gravity that almost everyone assumed would remain forever beyond our grasp. Where would such waves even come from? Gentle motions make ripples far too weak to notice. To stir spacetime detectably, you need enormous masses moving at tremendous speeds, and the most violent such events are the deaths and collisions of the densest objects in the universe. Two black holes spiraling into each other, two collapsed stellar cores, called neutron stars, crashing together. In those final moments, masses many times that of the sun whirl around each other hundreds of times a second before merging, and the space-time around them shudders with a force that sends a ripple across billions of light years. Even after that journey, the ripple arriving at Earth is barely there. But there was a tantalizing hint from before any wave was directly caught. In the 1970s, astronomers found a pair of neutron stars orbiting each other, and they watched the orbits slowly shrink, year after year, exactly as it should if the system were losing energy by radiating gravitational waves. The two stars were spiraling together at precisely the rate Einstein's theory predicted for waves carrying energy away. No one had detected the waves themselves, but here was their fingerprint, written in a decaying orbit. It was strong enough to earn a Nobel Prize, and it told the world the waves were real, even if we could not yet hear them. To hear them directly would take an instrument unlike anything built before, a machine designed to feel a tremor smaller than an atom in the fabric of space. Building it would consume decades, careers, and a fortune, and for most of that time it would detect nothing at all, while critics wondered aloud whether it ever would. The story of how we finally caught Einstein's waves, and what they revealed about gravity in its most violent form, is where our climb turns from the past toward the present, and toward the things that unsettle scientists today. The instrument is called LIGO, and the way it works is a small miracle of stubborn engineering. Picture two long tunnels, each about 4 kilometers in length, meeting at a right angle to form a giant letter L. A laser beam is split and sent down both arms, bounced off mirrors at the far ends and brought back to recombine. By comparing the two returning beams with exquisite care, the machine can detect if one arm has grown very slightly longer or shorter than the other. When a gravitational wave passes through, it stretches one arm and squeezes the other by a fantastically tiny amount, and the recombined light shifts in a way that betrays the wave's passing. The precision required is almost beyond belief. LIGO can sense a change in the length of its arms thousands of times smaller than a proton, which is itself far smaller than an atom. To reach that sensitivity, the builders had to silence the entire world. A passing truck, a distant earthquake, a crash of ocean waves on a far coast, even the faint patter of the laser's own light particles striking the mirrors. All of these had to be measured and subtracted. There are two such detectors, one in Louisiana and one in Washington state, thousands of kilometers apart, so that a real cosmic signal will strike both, while a local rumble will fool only one. The whole apparatus is a machine built to hear the universe over the noise of the Earth. The effort spanned decades and very nearly failed to win funding more than once. 3 figures anchored it. Rainer Weiss, who worked out the design of the laser detector in detail. Kip Thorne, the theorist who understood what the waves should look like and championed the search, and Barry Barish, the leader who turned a struggling project into a vast and disciplined collaboration of more than 1,000 scientists. For years the detectors ran and heard nothing, and skeptics asked whether the money had been wasted on a quixotic dream. Then, in September of 2015, almost exactly 100 years after Einstein finished his theory of gravity, both detectors twitched within milliseconds of each other. The signal was clean and unmistakable, a rising tone that physicists call a chirp, sweeping up in pitch and then falling silent. It was the sound, translated into something we can grasp, of two black holes, each around 30 times the mass of the Sun, spiraling together and merging into one, more than 1 billion light-years away. In the final fraction of a second, they converted an amount of mass greater than 3 suns entirely into the energy of rippling spacetime. For that instant, the collision shone, in gravitational waves brighter than every star in the visible universe combined. We had heard it. After a century of doubt, beginning with Einstein's own, the ripples in spacetime were no longer a prediction, but a measurement. Weiss, Thorne and Barish received the Nobel Prize in 2017, and a new way of sensing the universe was born. We had always studied the cosmos with light, with our eyes and our telescopes. Now we could feel it through the trembling of space itself, a sense entirely new to our species. This was a triumph for Einstein's gravity, one of the most exacting confirmations it has ever received. The shape of the chirp matched the theory's prediction beautifully. And yet listen carefully to what such a measurement also offers. For the first time we could test gravity not in the gentle setting of orbits and starlight, but in the most violent arena there is, where black holes collide and space-time is bent almost beyond endurance. If Einstein's theory was ever going to crack in a place we could watch, it would be here. The next signals would let us press on that question harder than ever before. The word for that breaking point is singularity, a place where the quantities in the theory shoot to infinity and the equations stop meaning anything. For a long time, physicists hoped the singularity was an illusion, an artifact of assuming a black hole was perfectly round and smooth. Real stars are lumpy and spinning, the reasoning went, so maybe a real collapse would miss the exact centre, swirl around, and avoid the catastrophe of a true point of infinite density. The singularity, they hoped, was a flaw in the idealised picture, not a feature of reality. A young British mathematician named Roger Penrose closed that escape route in 1965. Using a new and powerful style of reasoning about the shape of space-time, he proved that the singularity was not a fluke of perfect symmetry. Once a collapse passes a certain point and an event horizon forms, a singularity must follow, no matter how lumpy or off-centre or spinning the original star was. The infinite centre was not an accident you could dodge. It was woven into the logic of Einstein's own theory. For this work, Penrose received a share of the Nobel Prize in Physics more than 50 years later, in 2020. Then Penrose joined forces, in a sense, with a young physicist named Stephen Hawking, who turned the same powerful reasoning in the opposite direction, toward the beginning of time. If you run the expanding universe backward, everything grows denser and more curved until you reach the very first moment. Hawking showed that the same mathematics forcing a singularity at the centre of a black hole also forces one at the birth of the cosmos. The Big Bang, in this light, is not just a hot, dense early state. According to Einstein's gravity taken at its word, it is a singularity, a moment of infinite density where the theory once again breaks down and tells us nothing. Sit with how serious this is. Einstein's theory of gravity is one of the most successful descriptions of nature ever written. It explained Mercury, bent starlight, predicted the expanding universe, and conjured black holes that we have since seen. And yet that same theory, pushed to two of the most important places in all of physics, the centre of a black hole and the first instant of the universe, does not merely struggle. It self-destructs. It hands back infinity, which is mathematics raising its hands and admitting it has run out of road. This is the heart of why gravity remains unfinished business. A theory that predicts its own breakdown is telling you that it is not the final word, that something deeper must take over where it fails. Newton's gravity broke down in the small sliver of Mercury's orbit, and Einstein's richer theory grew out of that crack. Now Einstein's theory breaks down at singularities, and that crack is a sign that an even deeper theory of gravity must lie beneath it, one we do not yet have. There is a strange comfort hidden here though, and it is worth naming. The infinities are not where we live. The centre of a black hole is sealed behind a horizon, and the first instant of the universe is far behind us. For almost everything we care about, Einstein's gravity works flawlessly, and the breakdown stays safely out of reach. A bridge can be perfectly sound for crossing, even if it would fail under a weight no one will ever place on it. So the singularities did not send anyone into a panic. They were a known flaw, filed away as a problem for the distant future. What did not stay filed away was another prediction lurking in Einstein's equations. One he made, and then doubted, then made again. If mass curves spacetime and masses move, then the curvature should move too. Shake a heavy thing, and the bending of spacetime around it should ripple outward, like a disturbance spreading across a pond. Einstein predicted these ripples, called them gravitational waves, and then spent years unsure whether they were real or just a quirk of his mathematics. Settling that doubt would take a full century and an instrument of almost impossible delicacy. A gravitational wave is, at heart, a ripple in the shape of space-time itself, spreading outward at the speed of light. When two heavy objects whirl around each other, they stir the space-time around them, and that stirring travels off into the universe as a wave that alternately stretches and squeezes space as it passes. If such a wave washed over you, you would, for the briefest instant, grow very slightly taller and thinner, then slightly shorter and wider as space itself flexed. You would never feel it. The effect is unimaginably small. Einstein predicted these waves in 1916, soon after finishing his theory, and then spent 2 decades unsure. At one point in the 1930s he wrote a paper arguing that gravitational waves did not really exist, that they were a mathematical illusion. A journal editor sent the paper to a reviewer who found an error. Einstein was offended at the very idea of being reviewed, and he withdrew it in anger, only for a colleague to gently show him the mistake. The waves were real in the theory after all, but even Einstein doubted that anything so faint could ever be detected, and on that point he had good reason for doubt. The faintness is the whole problem, and it is staggering. By the time a gravitational wave from some distant cosmic violence reaches Earth, the stretching and squeezing it causes is smaller than the width of a proton across the entire span of a detector kilometers long. You are trying to measure a change in length thousands of times smaller than the nucleus of a single atom. For most of the 20th century, this seemed not merely difficult but absurd. A precision so fine that no instrument could ever hope to reach it. The waves were a beautiful consequence of Einstein's gravity that almost everyone assumed would remain forever beyond our grasp. Where would such waves even come from? Gentle motions make ripples far too weak to notice. To stir space-time detectably, you need enormous masses moving at tremendous speeds, and the most violent such events are the deaths and collisions of the densest objects in the universe. two black holes spiraling into each other, two collapsed stellar cores, called neutron stars, crashing together. In those final moments, masses many times that of the Sun whirl around each other hundreds of times a second before merging, and the space-time around them shudders with a force that sends a ripple across billions of light years. Even after that journey, the ripple arriving at Earth is barely there. But there was a tantalizing hint from before any wave was directly caught. In the 1970s, astronomers found a pair of neutron stars orbiting each other, and they watched the orbit slowly shrink, year after year, exactly as it should if the system were losing energy by radiating gravitational waves. The two stars were spiraling together at precisely the rate Einstein's theory predicted for waves carrying energy away. No one had detected the waves themselves, but here was their fingerprint, written in a decaying orbit. It was strong enough to earn a Nobel Prize, and it told the world the waves were real, even if we could not yet hear them. To hear them directly would take an instrument unlike anything built before, a machine designed to feel a tremor smaller than an atom in the fabric of space. Building it would consume decades, careers, and a fortune, and for most of that time it would detect nothing at all, while critics wondered aloud whether it ever would. The story of how we finally caught Einstein's waves, and what they revealed about gravity in its most violent form, is where our climb turns from the past toward the present, and toward the things that unsettle scientists today. The instrument is called LIGO, and the way it works is a small miracle of stubborn engineering. Picture two long tunnels, each about 4 kilometers in length, meeting at a right angle to form a giant letter L. A laser beam is split and sent down both arms, bounced off mirrors at the far ends, and brought back to recombine. By comparing the two returning beams with exquisite care, the machine can detect if one arm has grown very slightly longer or shorter than the other. When a gravitational wave passes through, it stretches one arm and squeezes the other by a fantastically tiny amount, and a recombined light shifts in a way that betrays the wave's passing. The precision required is almost beyond belief. LIGO can sense a change in the length of its arms thousands of times smaller than a proton, which is itself far smaller than an atom. To reach that sensitivity, the builders had to silence the entire world. A passing truck, a distant earthquake, the crash of ocean waves on a far coast, even the faint patter of the laser's own light particles striking the mirrors, all of these had to be measured and subtracted. There are two such detectors, one in Louisiana and one in Washington state, thousands of kilometers apart, so that a real cosmic signal will strike both, while a local rumble will fool only one. The whole apparatus is a machine built to hear the universe over the noise of the Earth. The effort spanned decades and very nearly failed to win funding more than once. 3 figures anchored it. Rainer Weiss, who worked out the design of the laser detector in detail, Kip Thorne, the theorist who understood what the wave should look like and championed the search, and Barry Barish, the leader who turned a struggling project into a vast and disciplined collaboration of more than 1,000 scientists. For years the detectors ran and heard nothing, and skeptics asked whether the money had been wasted on a quixotic dream. Then, in September of 2015, almost exactly 100 years after Einstein finished his theory of gravity, both detectors twitched within milliseconds of each other. The signal was clean and unmistakable, a rising tone that physicists call a chirp, sweeping up in pitch and then falling silent. It was the sound, translated into something we can grasp, of 2 black holes, each around 30 times the mass of the Sun, spiraling together and merging into one, more than 1 billion light-years away. In the final fraction of a second, They converted an amount of mass greater than 3 suns entirely into the energy of rippling spacetime. For that instant, the collision shone, in gravitational waves brighter than every star in the visible universe combined. We had heard it. After a century of doubt, beginning with Einstein's own, the ripples in spacetime were no longer a prediction, but a measurement. Weiss, Thorne and Barish received the Nobel Prize in 2017, and a new way of sensing the universe was born. We had always studied the cosmos with light, with our eyes and our telescopes. Now we could feel it through the trembling of space itself, a sense entirely new to our species. This was a triumph for Einstein's gravity, one of the most exacting confirmations it has ever received. The shape of the chirp matched the theory's prediction beautifully, and yet listen carefully to what such a measurement also offers. For the first time, we could test gravity not in the gentle setting of orbits and starlight, but in the most violent arena there is, where black holes collide and space-time is bent almost beyond endurance. If Einstein's theory was ever going to crack in a place we could watch, it would be here. The next signals would let us press on that question harder than ever before. The search for dark matter has been one of the great quiet labours of modern physics, carried out in some of the strangest laboratories on Earth, deep underground. The leading idea for many years was that dark matter is made of a new kind of particle, one that ignores light and the electric force but very rarely, very gently, bumps into ordinary matter. These hypothetical particles were given a name that doubles as a description: weakly interacting massive particles, shortened to WIMPs. If they are real, then trillions of them are streaming through your body right now, and through the whole Earth, almost always passing clean through, without touching anything. The hope was that, every so often, one would strike the nucleus of an ordinary atom and give it a tiny detectable nudge. To catch a nudge that rare, you must silence everything else. And that means going deep. The leading detector of recent years, called LUX Zeppelin, sits nearly a mile underground in an old gold mine in South Dakota, shielded by the rock above from the constant rain of cosmic particles that would otherwise drown the signal. At its heart is a tank holding 10 tons of ultra-pure liquid xenon, kept extremely cold. If a dark matter particle were to strike a xenon nucleus, it would produce a faint flash of light and a tiny puff of electrons, and the detector watches ceaselessly for that double signature. Similar experiments using xenon run in Italy and in China, all chasing the same faint hope. These are exquisite machines, the most sensitive instruments of their kind ever built, run by hundreds of scientists over many years. And here is the result, stated plainly, because honesty is the whole point. They have found nothing. In late 2025, the South Dakota team announced the most sensitive search yet, based on well over 400 days of data, the largest such data set ever gathered. No dark matter particle appeared. Decade after decade, as the detectors have grown larger and more sensitive, the WIMPs that were supposed to be there have simply not shown up. The region where they were most expected to hide has been searched and found empty. Worse, the search is running into a wall that is not about effort or money. As the detectors grow more sensitive, they have begun to pick up neutrinos, near massless particles streaming from the sun, which produce a signal almost identical to the one a dark matter particle would make. In 2025, the South Dakota detector caught these solar neutrinos for the first time, a real achievement, but also an ominous one. Physicists call this looming background the neutrino fog. Beyond a certain sensitivity, the fog of neutrinos will mimic dark matter so closely that telling them apart becomes nearly impossible. The hunt is approaching a haze it may not be able to see through. none of this proves dark matter does not exist. The gravitational evidence for it, the spinning galaxies, the bent light, the imprint in the ancient afterglow, remains overwhelming. The particles may simply be lighter or stranger or shyer than the WIMPs we bet on, and other searches continue for different candidates. But step back and feel the shape of the situation. We are certain, from gravity, that most of the matter in the universe is unseen. We have spent 40 years and enormous ingenuity trying to catch a piece of it directly, and we have caught nothing. The thing whose gravity holds every galaxy together has refused, so far, to reveal what it is. That silence sharpens the old, uncomfortable question we have circled since Mercury. Are we missing matter, or are we missing part of the law of gravity itself? The detectors coming up empty does not answer it, but it gives new weight to the other possibility, the one most physicists have long resisted. Perhaps galaxies spin too fast not because of invisible stuff, but because gravity does not behave, on the vast scale of galaxies, the way Newton and Einstein said it should. That rebellious idea has a name and a father. In the early 1980s, an Israeli physicist named Mordechai Milgrom looked at Vera Rubin's rotation curves and asked a question almost no one was willing to ask out loud. What if there is no missing matter at all? What if, instead, our law of gravity is simply wrong when the pull becomes extremely weak, as it does at the faint outer edges of a galaxy? Milgrom proposed that below a certain tiny threshold of acceleration, gravity stops following the familiar rule and grows stronger than expected, just enough to keep those outer stars whirling without any dark matter to help. He called his idea modified Newtonian dynamics, shortened to MOND. The striking thing about Milgrom's proposal is how well it works for galaxies, and how little it needs to do so. With a single new constant, one fixed number marking where gravity changes its behaviour, MOND reproduces the rotation curves of a vast range of galaxies, large and small, with remarkable accuracy. It even predicted features in galaxies that were only measured later. For the specific problem Rubin uncovered, the spinning of individual galaxies, MOND is in some ways tidier than dark matter, because it does not require you to sprinkle in just the right amount of invisible material in each galaxy by hand. The pattern falls out of one modified law. So why is MOND not the accepted answer? Because it succeeds beautifully on the scale of single galaxies and then struggles badly almost everywhere else. When you move up to great clusters of galaxies, MOND does not provide enough extra gravity on its own, and you have to add some unseen mass anyway, which spoils its main selling point. It has a hard time explaining the bending of light around clusters, the detailed pattern in the ancient afterglow of the Big Bang, and the way the largest structures in the universe formed over cosmic time. Dark matter, for all that we cannot find its particle, explains all of these at once, across every scale, with the same simple ingredient. That breadth is its great strength. There is one observation often held up as the hardest blow against MOND. When two galaxy clusters collide, we can map where the mass is by watching how it bends light, and separately map where the ordinary glowing gas is. In at least one famous collision, the two came apart. The gas piled up in the middle where the clusters smashed together, but most of the mass traced by the lensing sailed on ahead, separated from the gas. That looks exactly like dark matter, a substance that passes through the collision untouched while the ordinary gas slows down. It is hard to explain with a modified law of gravity alone, because in MOND the gravity should follow the visible matter, and here the gravity and the visible matter parted ways. Yet MOND refuses to die, and thoughtful physicists keep returning to it, because it captures something real. The fact that a single tweak to gravity nails so many galaxies so precisely is not nothing. It may be a clue that our law of gravity is incomplete in a way we have not understood, even if MOND in its current form is not the final answer. The deepest version of the debate is no longer a simple contest between unseen matter and a broken law. It is a suspicion that the truth may be some subtler blend we have not yet imagined. Hold both possibilities open then as honest live options. Either the universe is mostly invisible matter we cannot catch, or our law of gravity bends in ways we have not grasped, or something stranger than both. And just as that argument was heating up, the sky delivered a shock that made the whole puzzle far worse by revealing that gravity across the universe as a whole is not even winning. Through the 1990s, two rival teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone assumed it was slowing. The universe had been flying apart since the Big Bang, and gravity, the great attractor, should be gently pulling all that matter back together, putting the brakes on the expansion. The only question seemed to be whether gravity would eventually win and pull everything back into a collapse, or merely slow the expansion forever. To measure the deceleration, the team studied a particular kind of exploding star, a type of supernova that always burns with nearly the same true brightness, which makes it a reliable cosmic mile marker. By comparing how bright these explosions appeared with how far away they were, the teams could chart how the expansion had changed over billions of years. In 1998, both teams arrived at the same impossible answer, and it stunned them. The distant supernovae were fainter than expected, meaning they were farther away than they should be if the expansion had been slowing. The expansion of the universe was not decelerating at all, it was speeding up. Something was pushing the universe apart, overwhelming the inward pull of all its gravity, and that something was growing stronger as space grew larger. The leaders of the two teams, Saul Perlmutter, Brian Schmidt and Adam Riess, would share the Nobel Prize in 2011 for a discovery none of them had gone looking for. This was a genuine shock, and it deserves to be felt as one. For the whole history we have traced, gravity has been the force that pulls things together, that holds galaxies and bends starlight and crushes stars. Now the universe was revealing that, on the largest scale of all, gravity was losing. Some mysterious pressure was winning, prying the cosmos apart faster and faster. Whatever it was, it filled all of space, and it acted like a kind of anti-gravity, a repulsion built into the emptiness itself. And here is where a ghost we set aside walks back into the room. Recall Einstein's cosmological constant, the term he had added to hold the universe still and then renounced as his greatest blunder. That term described exactly this: a constant energy filling empty space, pushing outward. Einstein had invented it for the wrong reason, to freeze a universe he wrongly thought was static, and had thrown it away when Hubble found the expansion. Now, decades later, the accelerating universe seemed to demand it back, not to hold things still, but to drive them apart. The blunder was not a blunder, it was a description of something real that Einstein never lived to see. We gave this mysterious outward pressure a name: dark energy, echoing dark matter, and once again the name mostly marks our ignorance. When we tally up the universe's full contents, the result is humbling almost beyond words. Ordinary matter, everything that shines and everything we are made of, is only about 5% of the universe. Dark matter, the unseen stuff that holds galaxies together, is around a quarter. And dark energy, the pressure pushing space apart, makes up the remaining 70% or so. The overwhelming majority of the universe is two things we cannot identify, one that pulls and one that pushes, and both known to us only through gravity. So the picture is far stranger than spinning galaxies alone suggested. Gravity does not just hold things together. Played out across the whole cosmos, it is being beaten by a force we named only to mark that we do not understand it. And when physicists tried to explain that force, to calculate how much energy empty space should contain, they produced what may be the most embarrassing failure in the history of science. The failure is worth understanding, because it is not a small error, but a chasm. Our best theory of the very small quantum physics tells us that empty space is not truly empty. Down at the tiniest scales, the vacuum churns with restless activity, particles flickering in and out of existence too briefly to catch, a constant background fizz in the fabric of reality. This is not speculation. The fizz has measurable effects in the laboratory, and that churning vacuum should carry energy. Since dark energy looks like an energy spread evenly through empty space, the natural thought is that dark energy simply is the energy of the quantum vacuum, the fizz of empty space pushing the universe apart. So physicists calculated how much energy the vacuum should contain, and then compared it to how much dark energy we actually observe driving the cosmic acceleration. The two numbers should have matched. Instead, the theoretical prediction came out larger than the measured value by a factor so enormous it strains comprehension, a number with something like 120 zeros after it. This is not a near miss or a factor of a few. It is the single worst prediction in all of physics. A disagreement between theory and reality so vast that physicists sometimes laugh about it to keep from despairing. If the vacuum really held as much energy as the theory says, the universe would have torn itself apart instants after it began, and we would not exist. Something is profoundly wrong, and we do not know what. Either there is some hidden principle that cancels almost all of that vacuum energy with breathtaking precision, leaving just the faint trace we observe, or our understanding of the vacuum, or of gravity, or of how the two relate, is broken in a way we have not located. This puzzle is called the cosmological constant problem, and it has sat at the centre of physics for decades, unsolved it. It is one of the clearest signs that our theory of gravity and our theory of the small world do not yet fit together, because the very question, how much does empty space weigh, requires both at once and gives a nonsensical answer. It is worth pausing to take in how much of the universe we have now admitted we do not understand. We cannot identify the dark matter that holds galaxies together. We cannot explain the dark energy that pushes the universe apart. We cannot reconcile the energy of empty space with what we see by anything less than the worst error in scientific history. And all three of these mysteries are mysteries about gravity, about what pulls, what pushes, and what the emptiness itself weighs. The force you feel in your feet sits at the heart of the largest unanswered questions we have. For a long time, these were troubling but stable puzzles. We had a standard model of the universe, built on Einstein's gravity, with dark matter and dark energy added as ingredients, and it fit the data well enough to feel secure. Physicists could live with not knowing what dark matter and dark energy were, as long as the overall picture held together and made consistent predictions. The mysteries were deep, but the framework was steady, and steadiness is what lets science keep working in the presence of the unknown. What has changed recently, what has turned long-standing puzzlement into something sharper, is that the framework itself has begun to wobble. The careful measurements we trusted to pin down the universe have started to disagree with one another, not by sloppy amounts, but by margins too large to wave away. The first of these cracks concerns the simplest number you can ask about an expanding universe. How fast is it actually expanding? The number is called the Hubble constant, and it measures how quickly the universe is expanding today, how fast distant galaxies are flying apart for every unit of distance between them. It is one of the most important numbers in all of cosmology, because it sets the size and the age of the universe and underpins nearly everything else. And there are two excellent independent ways to measure it. The thing that has cosmologists genuinely unsettled, is that the two ways give two different answers, and the gap between them refuses to close. The first method looks at the early universe. The oldest light in the cosmos, the afterglow of the Big Bang, carries a detailed pattern, and from that pattern, combined with our standard model of how the universe evolves, you can calculate how fast space should be expanding now. The satellite that mapped this ancient light most precisely gives an expansion rate of about 67, in the units cosmologists use. This is the early universe answer, derived from the universe's infancy and then extrapolated forward to today. The second method looks at the nearby present-day universe directly. Astronomers measure the distances to relatively close galaxies using reliable mile markers, the same kind of stars and supernovae used to find the cosmic acceleration, and they watch how fast those galaxies recede. This local, hands-on measurement gives an expansion rate of about 73, faster than the early universe answer by a margin of several units. 6 or 7 units may not sound like much, but in this game it is enormous. Both measurements have grown more and more precise over the years, and as they sharpened. The hope was that they would converge on a single value. They have done the opposite. The error bars have shrunk while the gap stayed put, which means the disagreement has become more statistically significant, not less. Two of the best measurements in science, each refined to high precision, are confidently telling us two different things about the most basic feature of the universe. This is the Hubble tension, and it has hardened from a curiosity into a crisis. For years, many assumed it would dissolve as a mistake, some subtle error in one method or the other. The natural hope was that better instruments would expose the flaw and restore agreement. But the better instruments have only deepened the problem. The James Webb Space Telescope, the most powerful eye we have ever built, checked the local measurements with fresh precision and confirmed the higher, faster value. The early universe side has likewise held firm, reinforced by independent observations. As of the most recent assessments, in late 2025, the tension has not eased. The two universes, the early one and the late one, simply will not agree on how fast they are growing. Think about what a genuine unresolved disagreement here would mean. If neither measurement is wrong, then something is missing from the story that connects the early universe to the present one, and that connecting story is built on gravity. It would mean our standard model of the cosmos, the framework that has felt secure for decades, is incomplete in some fundamental way. Perhaps there is a new ingredient in the early universe we have not accounted for. Perhaps gravity behaves differently than we think over cosmic time. Perhaps dark energy is doing something we did not expect. The tension is a crack in the foundation, and through it, new physics may be leaking. And just as the Hubble tension was sharpening, a powerful new instrument turned its attention to dark energy itself, and brought back a result that, if it holds, would shake the framework even harder. It suggested that dark energy, which we had assumed was a fixed and constant feature of space, might be changing over time. The instrument is called the Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona, and it is a marvel of patient cosmic cartography. Its job is to measure the precise distances and positions of millions upon millions of galaxies, building the largest three-dimensional map of the universe ever made. Spread through that map is a faint regular pattern, a characteristic scale imprinted on the distribution of galaxies by sound waves that rippled through the hot plasma of the infant universe. That scale acts like a ruler laid across cosmic history, and by measuring how it appears at different distances, and therefore at different times, astronomers can trace how the expansion of the universe has changed, and how dark energy has behaved across billions of years. The simplest and long-assumed picture is that dark energy is a true constant, exactly the cosmological constant Einstein's renounced term describes, a fixed energy in empty space whose strength never changes. In that picture, dark energy was the same in the distant past as it is today and as it will be forever. This assumption sits at the heart of the standard model of cosmology, and for years all the data were consistent with it. Dark energy was mysterious, but at least it was steady. The recent results from the Great Galaxy Map have unsettled even that. When the team combined their enormous dataset with other measurements, the best fit was not a perfectly constant dark energy. The data leaned instead toward a dark energy that was somewhat stronger in the past and has been weakening over time. The pull of empty space, in other words, may not be a fixed feature of reality, but something that evolves, that was once more forceful and is now easing. The signal is not yet certain enough to call a discovery outright, and careful scientists stress that it could still soften with more data, but it has appeared across more than one data release and grown more interesting, not less, and it is the strongest hint yet that the simplest story is wrong. If dark energy really does change over time, the consequences are profound. The cosmological constant, the very thing Einstein's equations naturally accommodate, would no longer be the answer. Instead, dark energy would have to be some dynamic field evolving through the life of the universe, something not contained in our current theory of gravity and the cosmos as written. It would mean that the framework which has guided cosmology for a quarter century needs to be replaced or deeply revised. The same map also tends to pull the inferred expansion rate toward the lower value, which does nothing to relieve the Hubble tension and arguably makes the overall picture more strained. Stack these together and feel the weight of the moment. The expansion rate measured two ways will not agree. Dark energy, long assumed constant, may be changing. Dark matter, demanded by gravity, has never been caught. The energy of empty space comes out wrong by the worst margin in physics. None of these is a wild fringe claim. Each comes from careful mainstream measurement by large, sober collaborations. And every one of them is, at root, a question about gravity and how it governs the universe across space and time. This is what people mean when they speak of a possible crisis in cosmology. It is not that any single result has overturned Einstein. It is that the anomalies are piling up in independent places, all pointing toward the same suspicion that our theory of gravity and the cosmos is missing something important. And if you want the most quietly humbling sign of all that gravity remains unfinished, you need not look to the edge of the universe. You can look at the single number that describes gravity's strength, the constant Cavendish first measured, and find that to this day we cannot agree on what it is. Recall big G, the gravitational constant, the number that sets the actual strength of gravity, first measured by the reclusive Henry Cavendish with his lead balls and a thread. Of all the fundamental constants of nature, this is the one we have known the longest, because gravity was the first force we described with a law. You might expect, therefore, that we would know it with superb precision by now, polished over 2 centuries of effort. The reality is the opposite, and it is genuinely strange. Big G is the most poorly measured of all the fundamental constants, by a wide margin. Consider the comparison. Some constants of nature are known to 10, 11, even 12 digits, pinned down with a precision so fine it borders on the absurd. Big G is known to about 4 or 5 digits, and no further. The value sits near 6.67, with the rest in doubt. In an age when we can measure other quantities to parts per billion, we know the strength of the most familiar force in the universe to only a few parts in 10,000. For the force that holds you to the Earth, that is a remarkable confession of uncertainty. It gets worse, and this is the part that quietly worries the people who do the measuring. It is not simply that big G is hard to measure precisely. It is that different careful experiments, using different methods, get different answers, and the answers disagree by more than their own stated uncertainties allow. One team, using one type of apparatus, gets a value. Another team, using another, gets a value several error bars away. Each is confident in their own result. Each has hunted relentlessly for hidden mistakes, and still the numbers will not line up. When measurements disagree by more than they should, it means someone is making an error no one has found, or something deeper is going on that we do not understand. The effort to settle it continues, and it is heroic in its patience. A team in the United States recently completed a measurement of big G that took roughly a decade of work, refining a torsion balance much like Cavendish's in spirit, fighting every conceivable source of error. A team in China has measured G by 2 independent methods at once, precisely to expose any hidden bias. And yet, after all this, the situation has not cleanly resolved. The new measurements remain in tension with older ones, and the central mystery stands. The most basic number in the science of gravity is, after 200 years, still not nailed down. Most physicists believe the explanation is mundane, that there are subtle systematic errors in these experiments, undiscovered flaws in how the tiny forces are measured, and that one day a clever new method will reveal them and the values will converge. That is the sensible expectation, and it is probably right. But there is a small, lingering, less comfortable possibility that a few have raised, looking at the scatter of values over the years. What if big G is not perfectly constant? What if the strength of gravity varies, ever so slightly, in ways we have not understood? Almost no one thinks this is likely, and the evidence does not demand it. But the fact that the question can be asked at all, about the oldest constant in physics, tells you how unfinished our grip on gravity really is. So here is the honest reckoning. We cannot identify most of the matter. We cannot explain the energy of space. Our 2 measurements of the expanding universe disagree. Our dark energy may be shifting, and we cannot even agree on how strong gravity is in a quiet laboratory. Every one of these touches gravity, and beneath them all lies the deepest crack of all, the one we have circled since the centre of the black hole. Our 2 greatest theories, the one for gravity and the one for everything small, simply cannot be made to work together. We have 2 supreme theories of nature, and each is fantastically successful in its own domain. Einstein's general relativity describes gravity, the large and the heavy, the bending of space-time around stars and galaxies, and it has passed every test we have devised, down to the ringing of merged black holes. Quantum mechanics describes the small, the world of atoms and particles and forces inside them, and it too is confirmed to staggering precision, underlying all of modern technology. Each is among the best tested ideas in the history of science. The problem is that they describe reality in fundamentally incompatible ways, and when you try to force them together, the mathematics falls apart. In general relativity, space-time is smooth, continuous, and gently curving, a serene geometric stage that bends under mass. In quantum mechanics, everything is jittery, uncertain, and granular, with energy coming in discrete packets, and the vacuum itself churning with restless fluctuation. These 2 visions of reality do not merely differ in detail. they clash at the root. When physicists try to describe gravity in the language of quantum mechanics, to treat the curvature of spacetime as something quantum and jittery like every other force, the equations produce nonsense, infinities that cannot be tamed by the usual tricks that work for the other forces. The smooth stage and the jittery actors refuse to share one description. For almost everything we observe, this clash stays politely hidden, because gravity is so weak that its quantum nature never shows. In the everyday world, and even across most of the cosmos, you can use general relativity for the big and heavy and quantum mechanics for the small and light, and never make them meet. The two theories carve the universe between them and avoid each other's territory. The trouble comes only where something is both extremely heavy and extremely small at the same time, where strong gravity and the quantum world are forced into the same tiny region. And there are exactly two such places in all of physics. We have already named them both. The centre of a black hole, where a star's mass is crushed into a point, and the first instant of the universe, where everything that exists was packed into something smaller than an atom. In both, gravity is overwhelming and the scale is minuscule, so both theories are needed at once, and both used together collapse into meaningless infinities. At the two most important boundaries of existence, where things begin and where they end most completely, our physics goes silent. We do not have a theory that can describe them. We have two theories that each refuse to. This is the deepest reason gravity remains unfinished, deeper than any single anomaly. It is not that we are missing a measurement or a particle. It is that the very framework of physics is divided against itself, and gravity is the fault line. To describe the birth of the universe, or the heart of a black hole, or perhaps to truly understand dark energy and the weight of empty space, we need a theory that unites gravity and the quantum world into one consistent picture. Such a theory is called a theory of quantum gravity, and finding it is widely regarded as the greatest unsolved problem in all of physics. For nearly a century, since the days when the singularities first appeared, the finest minds in the field have hunted for it. They have built elaborate, beautiful, mathematically intricate frameworks and poured lifetimes into them. And here is the quiet, uncomfortable truth at the centre of that hunt, the one that turns a deep puzzle into a genuine source of unease. After all that effort, we still do not have the theory, and worse, we have almost no way to test the candidates we do have. There are two leading attempts to build a theory of quantum gravity, and they could hardly be more different in spirit. The first and most famous is string theory. Its central idea is that the most basic things in nature are not point-like particles, but tiny vibrating strings, far smaller than anything we can probe, and that the different particles we see, including the particle that should carry gravity, are simply different notes that these strings can play. String theory is mathematically rich and seductive, and for a time many physicists believed it was the clear path to uniting gravity with the quantum world. It naturally includes a quantum version of gravity, which is no small thing, and it has reshaped large areas of mathematics along the way. The second main attempt is loop quantum gravity, and it takes the opposite tack. Rather than starting with strings in a smooth space, it asks what happens if space-time itself is not smooth at all, but woven from tiny discrete loops, so that space comes in indivisible grains, a finest possible size below which the very notion of distance loses meaning. In this picture, the smooth stage of general relativity is an illusion that emerges from a finer, granular weave, the way a smooth cloth is really a mesh of threads. Loop quantum gravity tries to quantize spacetime directly, and it offers tantalizing hints, such as the possibility that the singularity at the center of a black hole might be replaced by something finite after all. Both are serious, the work of brilliant people over decades. and both run into the same devastating obstacle, the one that hangs over this entire field. We have no experiment that can decide between them, or test either against reality. The scale at which the quantum nature of gravity would become obvious is so extravagantly tiny, and the energies required to probe it so impossibly vast, that no accelerator we could ever build on Earth comes remotely close. The two theories make their boldest differences in a regime we cannot reach. So they have grown into towering mathematical structures with as yet almost no contact with measurement. In a science whose whole strength is the test, that is a profound and unsettling situation. This is where the new way of sensing the universe offers a thread of hope. When two black holes collide, they briefly create exactly the conditions where quantum gravity might leave a fingerprint, strong gravity in a violent dynamic setting. The gravitational waves we now catch carry information from that extreme arena. If a candidate theory of quantum gravity predicts even the faintest deviation from Einstein in the ringing of a merged black hole, then a sensitive enough detector might one day hear it. The scientists studying these mergers say openly that this is part of the hope, that someday a tiny departure from the expected tone will appear and point the way toward the deeper theory. It has not appeared yet. But for the first time, there is a place to listen, so the search goes on, partly in equations of extraordinary beauty, and partly now in the trembling of distant detectors. We have candidate theories without decisive tests, and a growing array of cosmic anomalies without a settled explanation, all converging on the same unfinished force. Which brings us at last back to the promise in our title. After everything we have built, from the weight in your feet to the edge of the cosmos, we can finally ask the question honestly. Are scientists really panicking about gravity right now? Or is that too strong a word for what is happening? Let us answer the title plainly, because honesty has been the rule of this whole journey. And the honest answer is more interesting than the dramatic one. No, scientists are not literally panicking. There are no physicists pacing the halls in terror, no field in collapse, no sense that everything we know is about to be thrown out. Einstein's theory of gravity still works beautifully wherever we can directly test it, from orbits to starlight to the ringing of black holes, and it will keep guiding spacecraft and explaining the heavens for as long as there is science. The word panic, splashed across a title, oversells the mood. That is the calm truth, and you deserve it. But quiet unease, a deep and growing disquiet among the people who think hardest about gravity, that is entirely real, and it is well earned. What unsettles physicists is not one dramatic failure, but a pattern, an accumulation. Set the pieces side by side. Most of the matter in the universe is unseen and uncaught, despite 40 years of searching. Most of the energy in the universe is a mystery we named only to mark our ignorance. The energy of empty space comes out wrong by the largest margin in the history of physics. Two superb measurements of the expanding universe stubbornly disagree. The simplest assumption about dark energy may be failing. We cannot even agree on the precise strength of gravity in a quiet room, and beneath it all, our two greatest theories cannot be made to speak to each other. Any one of these alone would be a fascinating puzzle that a confident science could carry. What creates the unease is that they are all happening at once, in independent corners of physics, and they all point inward toward the same suspicion. The framework we have trusted, Einstein's gravity stitched together with dark matter and dark energy, fits the universe well, but the seams are showing, in more than one place, and we cannot yet see what lies beneath them. This is the feeling that some honest scientists describe as a crisis, not because everything is wrong, but because the anomalies are no longer isolated, and the comfortable picture is straining. It is worth seeing this in the long view, because we have walked that view together. Newton's gravity was magnificent and complete until a sliver of Mercury's orbit refused to obey, and that sliver opened the door to Einstein. Einstein's gravity is magnificent and so far unbroken in every direct test, yet it predicts its own breakdown at singularities and cannot join the quantum world. The history of gravity is a history of beautiful, successful theories that turned out to be approximations to something deeper, each revealed by small, stubborn discrepancies that would not go away. The anomalies piling up today may be exactly that, the small, stubborn discrepancies that announce the next, deeper picture of gravity, the one we do not yet have. And there is genuine excitement folded into the unease, which is the part the word panic hides entirely. Moments like this, when the trusted framework wobbles and the anomalies cluster, are precisely the moments before great leaps. The crack in Mercury's orbit gave us curved spacetime and a new universe. The cracks visible now, in the dark sky and the disagreeing measurements and the divided theories, may be the openings through which the next revolution arrives. Physicists are not despairing. Many are exhilarated, because the universe is once again refusing to behave, and that refusal is the surest sign that something profound is waiting to be understood. So perhaps the deepest question is not whether gravity is in crisis, but what gravity, underneath all our pictures of it, actually is. And on that, the most radical thinkers have begun to wonder whether we have had the whole idea backward. For all of this story, we have treated gravity as something fundamental, a basic feature of reality, whether a force in Newton's hands or the curvature of space-time in Einstein's. But a small group of physicists has begun to ask a startling question. What if gravity is not fundamental at all? What if it is not a basic ingredient of the universe, but something that emerges from deeper things, the way the wetness of water emerges from molecules that are not themselves wet, or the way temperature emerges from the jostling of countless atoms that have no temperature of their own? The idea grows out of one of the most surprising discoveries about black holes. Stephen Hawking and others found that black holes have a temperature and an entropy, a measure of disorder, and that this entropy is tied not to the volume inside the black hole, but to the area of its surface, its horizon. That was a deep clue, because entropy is the language of statistics, of many hidden underlying pieces averaging out into the smooth quantities we see. It suggested that the smooth geometry of space-time might itself be a kind of average, a large-scale appearance arising from countless smaller pieces of information we cannot directly see, the way the smooth surface of a lake hides the frantic molecules beneath. This has grown into a serious line of thought sometimes called emergent gravity, and one physicist, Eric Valindi, has argued that gravity might be understood as something like a statistical tendency, an entropic effect, rather than a basic force. In this view, the reason masses draw together is related to the way a system naturally moves towards states of greater disorder, with gravity emerging from the bookkeeping of information in space-time. Bound up with these ideas is the strange and powerful notion of holography, the suggestion that everything happening in a volume of space might be fully described by information living on its boundary, as a flat hologram can encode a three-dimensional scene. If that is right, the three-dimensional space we live in, and gravity itself, might be a kind of projection from a deeper, lower-dimensional reality. These ideas are speculative, and we should say so plainly in keeping with everything else here. They are not established, they are not tested, and many physicists remain skeptical. But they are taken seriously by thoughtful people, and they hint at a resolution to our deepest crack. If gravity is emergent, a large-scale appearance rather than a fundamental force, then the reason it resists being turned into a quantum theory like the others might be that it was never one of the others to begin with. You do not quantize temperature by looking for a particle of heat, because temperature is already a statistical story about deeper things. Perhaps gravity is the same, and we have spent a century trying to quantize a shadow. Whether or not these particular ideas prove right, they capture the spirit of the moment we are in. The questions about gravity have grown deep enough that some of the answers being explored are not adjustments to the old picture, but proposals to replace the foundation entirely, to say that space-time and gravity are not the bedrock of reality, but ripples on the surface of something stranger. That is how far the frontier has moved, from arguing over a planet's orbit to wondering whether space itself is fundamental. We do not know which of these paths, if any, leads to the truth. We may be a few years from a breakthrough, or a few generations. But the direction is clear. Gravity, the most familiar force in your life, the one we have studied the longest, is leading us toward the most radical rethinking of reality that physics has attempted in 100 years. And so, having travelled all the way out to the edge of what anyone knows, we can return, at last, to where we began, to the simple weight in your own body, and see it with new eyes. Sit still again, and feel your weight, the same steady pull we started with. The chair holds you up, the floor holds your feet, and the whole earth draws you gently toward its centre. It is the most ordinary sensation there is, and you have felt it every moment of your life. We asked at the very beginning one plain question. When you let go of your keys, what is actually pulling them down? After everything, we can finally answer it. In the simplest words we have, nothing is pulling them. That is the answer Einstein gave us, and it has survived every test. The keys are not being yanked by an invisible cord. The Earth's mass has bent the shape of space-time around it, and most of all it has bent time, making time pass a touch more slowly near the floor than near your hand. The keys, simply moving as straight as they can through that bent space-time, drift toward where time runs slow, and we call that falling. Your weight in the chair is the floor refusing to let you follow that same natural path inward. You are not being pulled down, you are being held back from a fall you would otherwise take through the curve of time itself. That is the honest answer to the question we opened with, and it is beautiful. But we have also learned to hold it with humility, because it is not the whole truth, and the people who study gravity know it. The same theory that tells you why your keys fall breaks down at the centre of a black hole and at the birth of the universe. It cannot account for most of the matter that holds galaxies together, or the energy that pushes the cosmos apart, or why empty space does not weigh what our theories say it should. It cannot yet shake hands with the physics of the very small. The force you understand by feel is, at its foundation, the one we understand the least. So here is the truer landmark to carry away, the one sentence that holds this whole journey. The most familiar thing in your life is also one of the greatest unsolved mysteries in the universe. The weight in your feet right now connects directly to questions at the very edge of human knowledge, questions that may take the next great revolution in physics to answer. You do not have to travel to a black hole or the dawn of time to touch the unknown. It is already touching you, holding you to your chair every second, and there is something quietly wonderful in that. The universe did not hide its deepest puzzle far away in some exotic corner reachable only by giant machines. It placed it in the most common experience you have, the simple fact of having weight, of things falling, of being held to the ground. Every time you drop something and watch it fall, you are watching the one force that stitches together the cosmos and the one that still defeats our finest theories. The same force, the same fall, the same mystery. The strangeness was never elsewhere. It was always right here, in your own body, in the pull you stopped noticing long ago. The scientists are not panicking. They are doing something better. They are standing at the edge of what we know, looking at the cracks in the most familiar force there is, and feeling that particular excitement that comes just before the picture changes. We have been here before, with Mercury and Newton, and on the other side of that crack was a whole new universe. We may be standing at such an edge again. And it all begins where you are sitting now, with the gentle, patient, unexplained weight of being held to the earth.